In last class, I kind of quickly went through the essence of forward kinematics. But now what I'm going to do is I'm going to go back to drawing board and work out that whole problem step by step. The only takeaway, only thing that I want you to remember from last class is the rotation transformation matrix. Remember the one rotation transformation matrix that I derived? What was it? Cosine theta minus sine theta, cosine theta, all the non-diagonal terms 0, and at the end 1. That's the only rotation transformation that you should remember. And then there are 4 rules. 4 rules we talked about. Z-axis has to pass to the joint axis. Then the x-axis, xn, should intersect Zn and n minus 1. Then xn has to be perpendicular to Zn minus 1, and right-hand coordinate system to be followed. These are the only 2 things that you should sort of internalize for forward kinematics. Now I'm going to work out the problem. I'm going to work out half of the problem by hand, and the remaining part I'm going to use MATLAB. So if you have your laptops, computers, start MATLAB. And second thing is, if you haven't had any exposure to MATLAB, that is the reason why I gave a homework 1 assignment. My expectation is that you have some exposure to MATLAB. So remember, even though the course is 25 hours, if you just skip through and just take the quizzes, you should be able to do it in half an hour. But if you don't have any exposure to MATLAB, that is an opportunity for you to learn. So you have actually 2 weeks to finish those courses. MATLAB and Simulink is going to be very important in our class. Okay, so I'm going to start forward kinematics. Forward kinematics. And by definition, forward kinematics is given joint angles find x, y, z of end effector. And I'm going to start with a very simple robot. And first, let me draw the 3-dimensional figure for this simple robot. Now, this simple robot is one motor here. And on top of this motor, there is a link. Then there is this second motor. And then there is one more link. So this is the first motor. I'm going to call this motor 1. This is motor 2. And this is the 3-dimensional drawing, 3-dimensional representation. But first and foremost, I would like to draw the kinematic diagram. And this kinematic diagram is going to look something like this. This is the first motor. Then you have this second motor, which is represented as a joint. And then what you have is you have the end effector. So this is going to be the joint 1. This is going to be the joint 2. So this is going to be my frame 0. And let's identify, let me first write the rules. The rules are z-axis through joint. Second, xn is perpendicular to zn and zn minus 1. Third, xn must intersect zn and zn minus 1. And the fourth rule is right-hand coordinate system. These are the 4 rules. And first, I'm going to solve the problems that fit into these rules. And later, I will solve the problems wherein you have exceptions. And you will have to use additional frames and you have to use some tricks to solve the problems. But since this is our very first problem, I'm going to solve it step by step and everyone pay attention. So first, I'm going to use this as my Z1. Please understand. Actually, I'll call this Z0 because this is the 0th frame. This is the first frame and this is the second frame. Some of you may ask me, why not to start with frame number 1, 2, and 3? That is fine too. But if you read the robotics textbook, they always start with the 0th frame because this is considered as the inertial or the first frame. There is no frame before 0. So I would use X1, something like this. Now, please understand, next rule is I need to construct the triad with X, Y, and Z, right angle, X-axis, thumb, Y-axis, first finger, Z-axis, middle finger. So now Z-axis is coming towards us. There is no rule like whether the Z0 should be going up or Z0 should be going down. I just assumed it to be up, but that's totally fine. So now my basically Y0 is going to be something like this. Just check X, Z. Now Y0 is going towards this. Next thing, Z1. Okay, one second. You got X. So this is X, Y, Z. X, Z. Now Y is going towards the board. Use right hand. Any question about the sign convention? Yeah.
Shouldn't that be X0?
Oh, X0, yes. Of course. X0. Okay. Anything else? Okay. Next, Z1. Now, the thing is, following this rule, X1 has to be perpendicular to Z1. X1 has to be perpendicular to Z0. X1 should intersect Z1 and X1 should intersect Z0. And I would repeat once again. At this point, please understand that I have two choices. My X1 could be in the horizontal direction, which is in the same direction as X0, or my X1 could be in the direction of Y0. However, please understand, if I choose this as X1, what's going to happen is my X1, even though it intersects with Z1, it is parallel to Z0. There is this distance between these two. Can you see that there is this distance? So that cannot happen, which means my X1 has to be something like this. And once I have my X1 like this, check that X1 intersects Z1 and Z0. X1 is perpendicular to Z1 and X1 is perpendicular to Z0. Everyone understood this? Then I would finish the triad. Once again, X, Y, Z, X1, Z1, Y1. So this becomes Y1. Now, I need to place one more frame at the end effector, which is 0.2. So I would add Z2, X2, and Y2. Now I need to answer one question here. Please understand, frame number 2 does not have any joint. So it's not required that Z2 should be parallel to Z1, should be parallel to Z0. But it makes our life easy. As far as possible, if your frame number 0 is aligned with frame number 1, is aligned with frame number 2, calculation of projection matrices becomes very easy. So as far as possible, make sure that your frames are aligned as much as possible. Everyone understood this? This is the most important step. Next thing, what I'm going to do is, I'm going to add some link lengths. Clearly, this length, I'm going to call A1. This length, I'm going to call A2. This length, I'm going to call A3. And this length, I'm going to call A4. So now I have 4 link lengths, A1, A2, A3, and A4. Please understand that these link lengths are constants. They are not changing. They are constants. Now, let's start. What I'm going to do is, I'm going to write my first rotation matrix. Now, this is a very important step. The rotation matrix convention is going to be 0R1, which means 0 is the old frame, 1 is the new frame, and the joint angle, I'm going to call this theta 1, relates old frame to new frame. Once again, I want to tell you that when we are drawing the kinematic diagrams, theta 1 and theta 2 are zeros. Theta 1 and theta 2 in actual practice would change because the motor is going to rotate. As the motor rotates, theta 1 is going to change, theta 2 is going to change. But for the kinematic diagram, we are at the fully extended position when theta 1 is 0 and theta 2 is 0. So what that means is, this is your joint 1, this is your joint 2, this is joint 0, joint 1, joint 2. It's not like this, it's fully extended. And theta, once again, whenever you address theta, all the thetas, theta 1, theta 2, theta 3 will be positive. So which means if you curl your fingers in the direction of theta 1, your thumb is pointing towards Z0. Everyone understood this? If you curl your fingers in the direction of theta 2, thumb is pointing towards Z1. If you were to assume Z0 going down or Z1 going down, whole axis will be flipped. Okay? So be very careful. Theta 1 and theta 2, they should be in the positive direction. Yeah.
The fully extended position, like, will there still be the offset between Z1 and Z2, Z0 and Z1?
Yeah, fully extended. So basically, think about it. First joint, second joint, fully extended.
So the X1 won't intersect in any manner.
No, X1 would intersect because Z0 is actually infinitely extended. X1 is infinitely extended in the left hand side and right hand side. So X1 and Z0 will be intersecting. It's an axis. Z1 and X1 will be intersecting.
It's like axis along this.
Yeah, X actually axis goes left. You can actually extend. That is the direction of the axis, but you can draw axis something like this. So it's intersecting. So basically you can draw axis something like this. Same thing with Z1. Coordinate systems are extremely important. If you don't master the coordinate systems, your kinematics will go wrong. Kinematics goes wrong, dynamics will go wrong, dynamics goes wrong, controls will go wrong. And kinematics starts with appropriate selection of coordinate system. Everyone clear about the coordinate system? Now, what I'm gonna do is, and this is a very important step, I'm gonna go very, very slowly. My first step is I want to find out the rotation transformation between the frame number 0 and frame number 1. So this is my frame number 0. So I'm gonna write 0 R1. This relates, and please understand, for almost 99% of the problems, we are going to use only one type of rotation matrix. And that rotation matrix is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Everyone understood this? However, this is half of the story. The next part, I want you to remember, because this is the point where students sometimes, I myself make mistakes. Next part, this is the rotation matrix. And next thing is the projection matrix. So how did we derive rotation matrix? We used projection matrix to derive rotation matrix. So let me write this down. X1, Y1, Z1. This is the old frame. This is the new frame. Never ever forget this. Projection matrix. If you remember how we derived the rotation matrix, we derived rotation matrix using the projections. Now here, we are trying to relate two frames. The first frame, which is the initial frame, is x0, y0, z0. Next frame is x1, y1, z1. This rotation matrix is taking care of relative rotation between the frame 0 and frame 1. But there is no guarantee that x0 would be aligned with x1, z0 would be aligned with z1, and y0 would be aligned with y1. There is no guarantee. In this problem, it happens that way because this is the first problem, a simple one. But whenever you have any problem, rotation matrix is never going to change because our rotations are always going to be about z-axis. But the projection matrix will be different. For projection matrix, you will have old frame as the on the left hand side on the y-axis, and new frame on the x-axis. And now please pay attention, and this is extremely important. Understand x1. Is x1 aligned with y0? No. Projection of x1 on y0 is 0. Do you agree with me? Projection of x1 on z0 is 0. Do you agree with me? Since x1 and x0 are aligned and they are in the same direction, which is very important. X1 and x0 are in the same direction, so you have positive 1 here. There is a possibility that x0 could be going left side, x1 would be going right hand side. At that time, the sign would change. Yeah, hold on, but it depends upon who is where. So not yet. So right now, please understand, for this particular problem, projection of x1 on y0 is 0. Projection of x1 on z0 is 0. Check y1. Can you see? Now I want you to locate y1. This is y1. Projection of y1 onto x0 is 0. Projection of y1 into z0 is 0. Projection of y1 onto y0 is 1. Do you agree with me? Projection of z1 on x0 is 0. Projection of z1 on y0 is 0. Projection of z1 onto z0 is 1. Do you agree with me? Now, what we do is we multiply. Please understand, in this problem, this projection matrix is an identity matrix, which means even if you pre-multiply or post-multiply, you are gonna get the same result. Do you agree with me? Cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Do you agree with me? Okay. Now next part, and this is an important part, and this is explained in a very complicated way in all the robotics textbooks. Okay, so please pay attention here. Next part is I want to construct something called as the homogeneous transformation. This homogeneous transformation is a 4x4 matrix. This homogeneous transformation is a 4x4 matrix. The last row of this homogeneous transformation is always going to be 0, 0, 0, and 1. The last row of this homogeneous transformation is always going to be 0, 0, 0, 1. Now, this rotation transformation matrix, this rotation transformation will be part of this first 3x3 matrix. So this is going to be, I'm going to copy from here over here, sine theta 1, oh sorry, cosine theta 1, cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Everyone understood this? Now here is this column. And remember, this column gives you the translational relationship between the old frame and the new frame in the coordinate frame of the old frame. And I will explain this once again. Homogeneous transformation is the most important transformation that you need to figure out for forward kinematics. Homogeneous transformation comprises of two parts. One is the rotational relationship between the old coordinate frame, which is 0, and the new coordinate frame, which is 1, and translational relationship between the old coordinate frame and the new coordinate frame, which means we captured what is the rotation between 0 and 1. Now I need to find out what is the translation between 0 and 1. But it's extremely important. This translational relationship has to be valid for all the values of theta. What that means? Let me write this down and it will be clear. So I'm gonna say here, just bear with me for a second. There are 3 spots that I need to fill. Okay. This is the distance around x in the direction of x0. This is the direction, this is the distance y in direction of y0. This distance is the direction in z in direction of z0. Now please try to understand. There are 2 frames. There is 0th frame and there is first frame. 0th frame has x0, y0, z0. Everyone understood this? The first frame has x1, y1, z1. Everyone understood this? I want the distance between the 0th frame and the first frame in the coordinate frame of the 0th frame. So basically, I want to use the coordinate frame of the old frame. Now, I want you to look at it and just understand. In x0 direction, can I say that my distance here is 80, right? Or no? My x distance is A2. Yeah, A2. A2. Okay. But please understand, as that, and this is very important, think about it. As that theta 1 changes angle, that A2 is not going to remain A2. It could be A2 cosine theta. So which means when theta 1 is 0, this becomes A2. This becomes 0. But if my theta 1 is say 90 degrees, this will become 0 and this will become A2. In other words, if I want that relationship to be valid for all the values of theta, this would be A2 cosine theta 1, A2 sine theta 1, and this would be just A1. Now, one thing, it's please understand, I'm trying to find out the x distance in the direction x naught, which means I want you to notice that A2 is written positive, because please understand frame number 2 is along x naught by distance A2. That's why it's positive. Everyone understood this? Otherwise, the sign here is very important. Sign here is positive because if you look at the distance between the 0th frame and the first frame with the coordinate system x0, y0, z0, A2 cosine theta 2 is positive, A2 sine theta 1 is positive, and A1 is positive. Everyone understood this? So, yeah.
Sir, please repeat about A2 cos theta.
Correct. Correct. So now what I want you to do is, I want you to look from top. So if you look from top, you agree with me, this is going to be the frame. X0, Y0, and Z0 is coming towards you. Do you agree with me? Now understand, when theta is 0, this becomes your A2. When theta is non-zero, this becomes A2 cosine theta 2 and A2 sine theta. Theta 1, sorry. Sine theta 1, correct. Everyone understood this? But z distance, there is no angle, it doesn't matter. It's always going to be at A1. This is the most important transformation. Okay, this is called as the homogeneous transformation. Homogeneous transformation includes the orientation information and it includes the translational information. Believe you me, once you master homogeneous transformation, you will solve any three-dimensional kinematics problem, because our world is only 3 dimensions. So once you understand, the same transformation would come in when you look at UAVs, UGVs, UUVs. Please understand the frame 0 and frame 1 are related with this rotation transformation, and those are the relative translations. Yeah.
What's the purpose of the bottom row?
Oh, bottom row, so that the math works out. Because finally we are going to multiply 4 by 4, 4 by 4, 4 by 4. And let me tell you, this is not the most sophisticated way of doing it. If you took the same class as an undergraduate student, I exclusively use rotation transformations. But there is an elegant way of doing it, which is called as quaternions. So we will talk about quaternions once we finish the rotation transformations. Yeah.
So is this applicable for all 2R robots or just like the 2 parallel R?
Any robot. just doesn't have to be 2R robot. It could be RP, PR, RS, SR, or you can do it for the UGVs where there is no ground link. Well, you imagine a hypothetical ground link that extends.
So solving this still wouldn't give us the value of the end effector.
Right now, it's actually giving you the value of end effector. If I substitute the value of theta 1, I know what is the X position of the end effector that is located at frame 1. If your end effector is here, you basically got the translational positional information. But this is not the end of the story.
Yeah.
This is actually the beginning. Yeah.
What actually is the homogeneous matrix?
Homogeneous transformation matrix is the relationship between the two frames describing orientation and translation. That is the definition of homogeneous transformation. And if you read a book, there will be 5 pages talking about homogeneous transformation. But yeah.
Will there be any constraint on theta?
No constraint on theta. Theta can be 0 to 360 till now. See, I tell you, the beauty of rotation transformation and Cottonian is it can handle singularities beautifully. DH parameters, they do not. So if you open any textbook on robotics, they will talk about something called as Danavet-Hartenberg parameters. It's an elegant way of solving, but it does not work for all the problems. And I'm going to explain DH parameters because that's all the books talk about. But then I'll show you the cases where DH parameters do not work. And to address that, they came up with modified DH parameter. So my question is, why use DH and modified DH when you have rotation transformation that will work for all the problems, not only articulated robot, UGV, UAV, any, if you take my robotics 2 class, you will see the same matrix. So we will understand this concept very well. This is what I would recommend. We would solve problems using this. Then I will show you how the problem is solved using DH parameters. Then we will look at the cases when the DH parameter fails, but rotation transformations work. And then we will go to the granddaddy of all, that is Cottonians. That is how the actual robot kinematics is done. And screw theory. Yeah. Any other questions?
So let's say there's a Y offset as well between the first 0th frame and the first frame. So there will be another term in the.
We will talk about those cases later. This is the first problem. We are going to have a lot more problems. There will be offset, there will be inclined links, the hinges, which are spherical links. Don't worry about it.
Angle 2 is not rotating, right?
Right now, it's not rotating.
Only angle 1.
Yeah, we are going to angle 2 right now. So same approach. Yeah.
Is the frame 2 fixed with the joint 2 or is it like moving along with the joint?
So when you say frame 2, it's fixed with the joint but rotating with the joint. You see what I'm saying? It is rotating with the joint. So it's not inertial frame. It's rotating with the joints. That's what. So if theta changes, that frame will also change with theta. That's what it means. Okay, next part. So now I need to go from 1R2. Same approach. My rotation matrix is going to remain the same. Sin theta 1. Yeah, correct. Theta 2 and theta 2. 0, 0, 0, 1. Now, let's not forget, we have one more matrix, which is the projection matrix. Same thing, old frame is x1, y1, z1. New frame is x2, y2, z2. Now look at x2. x2 is aligned with x1. y2 is aligned with y1. z2 is aligned with z1. Do you agree with me? So instead of spending time, can I just write this like 0, 0, 0, 1, 0, 0, 0, 1? This matrix is extremely important. Never forget this. Everyone understood? Projection of x2 on y1 and z1 is 0. Can you see? Because x2 is going in this direction, z1 and y1 are perpendicular to x2, so you cannot have any projection. X2 is only aligned with x1. It is in the same direction. That's why it's positive 1. Y2 is aligned with y1, same direction. That's why it's positive 1. Z2 is aligned with z1, same direction. That's why it's positive 1. So when I make this multiplication, this is an identity matrix. I get cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Are you with me? Now I need to populate the homogeneous transformation 1H2. 1H2, remember this will have 0, 0, 0, 1. And this rotation transformation will go here, cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Now here, I'm gonna rewrite this. This is the distance x along x1, distance y along y1, distance z along z1. Because please try to understand, the old frame is 1, the new frame is 2. You are going from old frame to new frame. So you are going from 1 to 2, not from 2 to 1. You are going from 1 to 2. So you will be traveling along x1, along y1, along z1. And again, can I say, again, using the same logic, my x distance is going to be a4 cosine theta 2, a4 sine theta 2, and last one is a3. And do you see all these are positive? You agree with me? Okay. With this, forward kinematics problem is solved. Check this out. 0H2 is actually the forward kinematics problem. How do I go from 0th frame, which is my very first frame, to the second frame? I go with 0H1 multiplied by 1H2. Do you agree with me? I have 0H1, which is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and it comes from A2 cosine theta 1, A2 sine theta 1, A1 multiplied by cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0. Last part, A4 cosine theta 2, A4 sine theta 2, A3 and 1. You agree with me? Now what's going to happen? I have this 4 by 4 matrix. When I multiply this by 4 by 4 matrix, I'm going to get a very long 4 by 4 matrix. But we are not doing this calculation by hand. We are going to use MATLAB. But what's going to come out of it is finally you are gonna get this big 4x4 matrix. And this is extremely important. This 4x4 matrix would also have the same structure. This 4x4 matrix would have something like 0, 0, 0, 1. And since I'm multiplying, I will get some rotation matrix here. This 0 H2 will give me 0 R2 and the translational distances x 0 2, 0 Y2 and 0 Z2. Are you with me? So after I do this multiplication using MATLAB, what I'm gonna get is I'm gonna get 4x4 matrix. This 4x4 matrix would have the same structure as 0R1 or 1R2, but this matrix will have theta 1 and theta 2 because now there are two angles involved. And this will have theta 1 and theta 2 because now the total distance includes A1, A2, A3, A4 and theta 1 and theta 2. Everyone understood this? But at the end, this is the structure. And again, I used to do this by hand. But then I said, I'm too old to do this by hand and I'm going to use MATLAB. So please use MATLAB if you are with me.
Can I say that 0x2 is the distance of an effector from the first
Zeroth frame.
0.
There is something else too. Okay. Look at the way I have defined the homogeneous transformation matrix. This x2 means x distance between, and very important, frame 2 okay, distance between frame 2 and frame 0, extremely important, along x0. Y distance between frame 2 and frame 0 along y0, and z distance between frame 2 and frame 0 along z0. Because please understand, this is your anchor. You are going to frame 2 with respect to frame 0. So the distance between frame 2 and frame 0 is along x0, y0, z0. Everyone understood this? Okay. Okay, so what I'm gonna do is I'm gonna share my MATLAB screen. This is my MATLAB. So somewhere like that. Yeah. And I strongly recommend that if you have laptops, please pull MATLAB. And start coding. At least look at how I code, and I'm sure you'll find some mistakes. So we are gonna use symbolic algebra. So I'm gonna say SYMS. My variables are A1, A2, A3, A4, and then I'm gonna call TH1 and TH2. I'm calling them to be symbolic variables. MATLAB would never allow me to start a matrix name with a number. So I'm gonna call 0H, so H01, because MATLAB will not allow me to define 0H1. H01 is going to be cosine TH1, okay, then sine minus sine th1. Oh, then I have 0. Then I have a2 multiplied by cos th1 semicolon. Then I need to go to the next. Actually, let me be more specific. 1, 2, 3. So I can go on to the next line. Make it look prettier. Sine th1 comma cosine th1. I'll forgot a comma here just to be for consistency. I'll add a comma. 0, comma, and I have a2 times sine th1 semicolon and so on. Last 0, comma 0, comma 0, comma a1 and so on, and last 0, comma 0, comma 0, comma and 1, and then I'll finish it over here. Yeah. Oh yeah. First, so here, yeah. Okay, I know you will find some mistakes. Copy. Paste. Now, in this particular problem, everything is easy. Theta 2. No, MATLAB is becoming too smart. Theta 2. Yeah, I don't want arcs. So this becomes A4. Theta 2. Cosine sine theta 2. A4. Make it look nicer. And then this becomes A3. Okay, did I get it right? Oh yeah, there is some this is MATLAB added ARX. Yeah, H12, correct. Anything else? See, backside driving is always fun, right? Try real-time coding. And then what I would do is H02 is equal to H01 multiplied by H12. Now the problem here is once you do this multiplication, you are gonna get a very, very complicated and long equation. So I'm gonna try to do this simplification. So I would say simplify. And just simplify so that it will combine the terms and give me a very small expression that is easier to interpret. Because what I want to show you is whatever solution you get from forward kinematics, it needs to make sense. Because if your calculations are wrong, then looking at the solution, you should see that, hey, something is not right. So-
To write a dot before that multiplication sign.
It's not dot multiplication.
No, because the matrix multiplication in MATLAB, I think that happens that way.
Okay, try dot. Let's start, just start with star and then we'll try dot. Okay, now I'm gonna say evaluate expression. Oops. And clearly you will go to command window. And this is my command window. Now, I want you to think carefully what these terms are telling me. There is one student online. So what I'm gonna do is I'm gonna start my video because I'm gonna explain something on the board. And I want you to have this expression in front of you and you should be able to see the board. Okay, now I want you to understand. The whole problem started with something like this. This was my motor 1. This motor 1 had this link. At the end of this link, there was this motor 2. This motor 2 was fixed to motor 1. There was this motor shaft, and then this is how the problem was set up. And these were our coordinate frames. Z0, and I'm drawing perspective, so it may be little C1, Z2. Here, theta 1. Here, theta 2. These distances, A1, this distance, A2, this distance, A3, this distance, A4. Now I want you to look at the coordinate frames the way we have drawn over there. This is x0 and my y0 is going like this. This is my z0, z1, this is my x1, my y1 is going like this. z2, x2, and my y2 is going like this. Everyone understood this? Now, at the end, I got this matrix. What this matrix tells me is if I look at the first 3 by 3, that gives me the relative orientation of the frame number 2 with respect to frame number 0. This is my frame number 0. This is my frame number 1. This is my frame number 2. And this interpretation is extremely important, because at the end of every kinematics problem, you should do a sanity check if these answers make sense. First, what I want you to ask yourself, everything is with respect to the 0th frame, because our base frame, this is going to be my base frame. Everything is calculated with respect to my 0th frame. Everyone understood this? All the distances, all the angles are with respect to 0th frame. Look at frame number 2 for a second. If theta 1 is 0, theta 2 is 0. If theta 1 is 0, theta 2 is 0, do you agree with me that frame number 2 and frame number 0 are perfectly aligned?
Yes. Yes. Yes.
And that's what this shows. When I say they are perfectly aligned, okay, when they are perfectly aligned, what is the rotation matrix between the frame 0 and frame 1? Identity. So if I substitute theta 1 as 0, theta 2 as 0, this term becomes 1. Theta 1 0, theta 2 0, this term becomes 0. This term becomes 0. This term becomes 1. So can you see that my first 3x3 matrix is going to become identity? Now what that means is if I add a, if theta 2 is 0, if theta 2 is 0, orientation of frame 2 will be same as theta 1. If I have theta 1 and theta 2 both, what that means is the relative angle between these two will be theta 1 and theta 2. Understand? I want you to look at this problem from here. And once you look, you are going to see the first joint, which is Z0. So you are going to see X1, X0. You are going to see Y0. And check this out. This is going to be your theta 1. Okay. Now, there is a thing that I want you to understand. Now, you extend this. And now you have this link number 2. This angle is theta 2. This is your frame number 2. So I'm going to, if I call this EE, this is going to be my end effector. So what this means is the angle of the end effector would be theta 1 plus theta 2. Do you agree with me? Yes. That's what that shows. The angle of end effector would be theta 1 plus theta 2. Now I'm going to say this is going to be A2. This is going to be A4. And I'm going to draw this, extend this. This is going to be A2 cosine theta 1. This is going to be A4 cosine theta 2. This guy is going to be A2 sine theta 2. And this guy is going to be A4 sine theta. So the total, again, everything is with respect to x0. This is x0. This is y0. Which means the end effector position is A2 cosine theta 1 plus A4 cosine theta 2 above x0 axis. This is the x distance. 0, 2. 0, y2 distance is A2 sine theta 1 plus A4 cosine theta 2. That is about y0. And the last 0, z2, again, that is nothing but A1 plus A3. Because that is the distance between this guy. That does not change. This is A3. This is A3 and A1. A3 plus A1. So check this out. What you got is you got
They're not matching.
yeah, they are not matching because cosine theta 2, so cosine theta 2 plus theta 1. As you can see, your theta is with respect to this, so this is going to be sine theta 1 plus theta 2. Yeah. So this angle, when you are trying to find the projection, please note you are finding the projection with the horizontal axis. This angle is theta 2, but this length is making theta 1. So the total angle made by A4 is theta 1 plus theta 2. So this becomes A4 cosine of theta 2 plus theta 1, A4 sine of theta 1 plus theta 2. Now are the answers matching now? So at the end, the solution that you get from the forward kinematics is the same solution that you get from the geometric analysis. So just making sure that. So that is the forward kinematics. In next class, I would work out the problem wherein you have the first revolute joint. So this is called as R parallel R. R parallel R. If you keep on adding parallel links, this expression, this will become theta 2 plus theta 1, theta 2 plus theta 1. And basically, if you start adding parallel joints, you will have theta 1 plus theta 2 plus theta 3, theta 1 plus theta 2 plus theta 3, and the link there. Okay, so I'm going to stop here, but I will answer any questions that you may have.
Sir?
Yeah.
Sir, this is a very basic problem. Because Z1 is aligned to Z1. So, sir, if there is a problem where Z1 is not aligned to Z0,
Yeah, we will solve those problems.
and sir, there are two frames. What is the maximum number of axes more than a robot? Getting to 21 and that you have to find.
MATLAB. This whole process can be automated in MATLAB.
Again, this, we have to assume that theta 1 and theta 2 are in the same direction, right?
The same direction, they should be positive with respect to positive Z naught
It
and
is possible that we come across scenarios when both of them are moving opposite to each other in direction.
yeah, it's possible. Then you change the sign to minus, and that will solve the
Sign
problem.
of this whole angle or the
Yes, angle sign.
angle inside theta